Tonight, we are going to talk about a star that does not have to touch Earth to become dangerous. It does not need to swallow our planet, pull us apart, or drift anywhere near the solar system. From the right distance in the wrong direction, a dying massive star could send out a flash so powerful that Earth would never feel it as heat, wind, or fire. The sky would not explode. The oceans would not boil. Most people would see nothing at all. And yet, high above us, the atmosphere could begin to change. The invisible shield that protects life from the sun could be damaged by radiation that crossed space for thousands of years before it arrived. That is what makes this story so unsettling. The danger is not a monster flying toward us. It is a beam, a narrow, violent lighthouse from the death of a star aimed across the galaxy. And if Earth were ever in the path of one close enough, the planet below it could be changed without warning. Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the universe. And write in the comments where you are watching from and what time it is where you are right now. It is strange to think that people are listening from different parts of one small planet at different hours, while the same stars move silently above all of us. Tonight, you are watching the Space for Sleep channel, talking about the star that could destroy Earth from light years away. When people imagine the universe destroying Earth, they usually picture something with a shape, a rock in the dark, a planet knocked loose from its orbit, a black hole wandering too close to the sun. Even the word disaster makes the mind reach for something physical, something you could point a telescope toward and say, there it is. That is the thing coming for us. It makes sense. The most famous cosmic threat in modern memory was an asteroid. 66 million years ago, a body roughly the size of a city struck what is now the Yucatan Peninsula, and the world changed. Dust rose, sunlight faded. Life was pushed into a different future. So when we look upward and think about danger, we often look for the next object, something falling, something drifting inward, something large enough to cast a shadow before it arrives. Black holes fit that fear almost too perfectly. They are invisible mouths in space, regions where gravity becomes so strong that even light cannot escape. A black hole sounds like the final answer to every cosmic nightmare. But black holes have one comforting quality. For most of the universe, they are not hunters. A black hole does not cross the galaxy like a monster searching for planets. It does not reach across many light years and pull ordinary stars out of the sky. Gravity weakens with distance. Unless something passes very close, a black hole can sit in darkness for billions of years while the rest of the galaxy moves around it. That is why the danger is local. To be destroyed by a black hole, Earth would have to come near one, or one would have to come near Earth. The event would be enormous, but it would also have geometry. There would be an object, a path, and a distance, closing over time. The danger in tonight's story is different. It does not need to arrive as a rock. It does not need to pull the oceans into the sky. It does not even need to be visible before it matters. The star could be nowhere near us. It could sit thousands of light years away, buried among other points of light, harmless for most of its life. It might appear as just another distant source in a catalogue. Then, under rare conditions, its death could become directional, not an expanding shell of material reaching us like a wave. Not a supernova blast physically sweeping through the solar system. A beam, a narrow release of energy, focused into space, moving at the speed of light. That is, the threat distance does not fully erase. If the beam is aimed elsewhere, Earth is safe. If it is aimed toward us, and close enough, the first warning could be the light itself arriving. No rumble would pass through the ground. No wall of flame would roll across the continents. The moon would not shatter. The sun would not flicker. Most people would never see a bright object appear overhead. The damage would begin above the weather, in a region of the atmosphere that rarely enters ordinary thought. The upper air would take the hit. Molecules would be broken and rearranged. Chemistry, not impact, would become the disaster. That is harder to picture than an asteroid, which is partly why it feels less real. A crater is easy to understand. Radiation arriving from a dying star is not. Yet the universe is full of dangers that do not resemble the ones our senses evolved to recognize. Human beings are built to fear the thing moving in the trees, the storm on the horizon, the fire spreading toward the house. We are not built to fear a flash of high-energy light that crossed the galaxy before touching a layer of ozone we cannot see. Still, that invisible shield is one of the reasons complex life can live on land at all. The atmosphere is not just air to breathe. It is armor. It absorbs harmful radiation, slows incoming particles, scatters sunlight, and wraps the planet in a chemical barrier between biology and space. Life on Earth feels solid because that barrier works quietly. We walk under blue sky and rarely remember that the sky is doing anything. A dangerous gamma-ray burst would turn that quiet protection into the center of the story. The flash itself would be brief. Its importance would not come from how long it appeared on a clock, but from what those seconds did to the chemistry above us. That is why this threat is so unsettling. It is not a movie explosion. It is a delayed wound. The radiation would be absorbed high overhead, and in absorbing it, the atmosphere could change. Nitrogen and oxygen, normally the familiar ingredients of air, could be forced into new reactions. Ozone could be depleted. More ultraviolet light from the sun could reach the surface afterward. The star's death would be over, but Earth would keep living with the consequences. A disaster like that would not feel like the end of a world in a single instant. It would feel like the rules of the sky had been altered. Plants, plankton, shallow water life, exposed animals, and entire food chains could be pushed under stress by something that never touched the ground. The sun, which life depends on, would become more dangerous because the filter above Earth had been weakened. The star itself would not have to cook the oceans. It would not have to burn forests from light years away. The danger would be indirect, and indirect dangers are often the easiest to misunderstand. They sound weaker until you realize that ecosystems can collapse through pressure, not just impact. This is also where the title needs care. A star that could destroy Earth from light years away does not mean a star that is definitely about to do it. It does not mean astronomers have found a nearby object aimed at us with a countdown attached. The real idea is more careful and more interesting. There exists a kind of stellar death that can send extreme radiation through space in a narrow direction. If a burst like that happened close enough, and if Earth were inside the beam, the consequences could be severe. Those conditions are specific. The event is rare. Alignment matters. Distance matters. The kind of star matters. Science becomes weaker when we skip those details. So we will not skip them. The goal is not to pretend the galaxy is filled with hidden guns pointed at Earth. Most explosions happen too far away. Most beams point somewhere else. The sky looks calm because, for us, it usually is. But calm is not the same as empty. Across the Milky Way, massive stars are burning through their fuel. Some will end as neutron stars. Some will collapse into black holes. A few may die in ways that launch jets through their own collapsing bodies, cutting tunnels out of the star and escaping into space as some of the most energetic flashes known. From far away, such an event may appear as a gamma-ray burst. For a distant galaxy, it is a signal. For a planet in the wrong place nearby, it could be an atmospheric crisis. Power alone can mislead us. A supernova releases an almost unimaginable amount of energy, but most of it spreads outward in all directions. The farther it travels, the more thinly that energy is spread across space. By the time it reaches a distant world, the force may be too diluted to matter in a catastrophic way. A beam changes the calculation. Concentrate energy into a narrow path, and distance begins to behave differently. Not magically, not without limits, but differently enough that a remote star can become relevant if its violence is focused toward one small target in the dark. Direction can matter as much as distance. That is the idea our instincts often miss. When we hear that a dangerous star is thousands of light years away, the mind relaxes. Thousands of light years sound safely outside the scale of human concern. No spacecraft can cross it. No explosion from ordinary experience can bridge it with meaningful force. A star at that distance feels like background. But light crosses that distance easily. Radiation does not need a road. If a massive star died long ago and aimed a jet toward our part of the galaxy, the effect would not arrive when the star died. It would arrive when the light reached us. The source could already be gone. The explosion could be ancient. Somewhere in the galaxy, the event would be over, while here, on Earth, its message would still be on the way. That separation between cause and arrival is one of the quietest horrors in astronomy. A civilization can rise under a peaceful sky, while a flash from an old catastrophe is still crossing the dark between stars. Nothing about the night would necessarily warn them. Then the signal would arrive at the speed of light, not as a visitor, but as the first and only announcement. Of course, the word destroy needs care. Earth would not be erased as a physical planet. The rock would remain. The oceans could remain. The question is whether the living surface could be pushed into a global crisis. That is the kind of destruction this story is about. Not the disappearance of Earth, but the disruption of the conditions that make Earth familiar. The sky stays blue, but the blue sky no longer protects in the same way. This is why gamma-ray bursts belong in the same conversation as asteroids, supernovae, and other rare cosmic hazards. Not because they are likely tomorrow, not because fear should replace perspective. They matter because they show that the universe has more than one way to reach a planet. Gamma rays are not ordinary brightness. They are high-energy radiation, able to ionize matter and force reactions in the molecules they meet. So the danger is not that a star is bright. The danger is that a dying star can release the wrong kind of light. High-energy light. Light that does not behave like sunlight at sunset. That is the doorway into tonight's subject. Not panic, not prophecy. A mechanism. A star lives, burns, collapses, and dies. Most of the galaxy barely notices. But in the final seconds of the right kind of death, energy can be forced into a narrow channel. If that channel escapes the star and points into space, it becomes a cosmic lighthouse. If Earth is not in the beam, the lighthouse shines elsewhere. If Earth is inside it, the distance between safety and danger is suddenly measured not by whether the star is near, but by whether the beam arrives strong enough to alter the sky. To understand how such a thing can happen, we need to move backward from the beam to the star that creates it. Not every star can die this way. The Sun cannot. A small red dwarf cannot. Even many massive stars will end without producing the kind of burst that matters here. The dangerous path requires a very specific life. Enormous mass, furious burning, instability near the end, and a core that fails in a way ordinary matter cannot survive. So before we talk about the flash that could cross light years, we have to look inside the star itself, into the place where the disaster begins, long before anyone on Earth could ever see it. At first, a star like this does not look like a weapon. For most of its life, it looks like a furnace. A massive star forms inside a cold cloud of gas and dust, where gravity slowly wins over pressure, turbulence, and magnetic fields. The cloud tightens. Fragments collapse. Somewhere inside one of those fragments, the center grows hot enough for hydrogen nuclei to begin fusing into helium. A star switches on. From the outside, that can sound peaceful. But A massive star is beautiful in the same way a wildfire is beautiful. Its brightness comes from violence, held in balance. Gravity wants to crush it inward. Fusion pushes outward. For a while, those two forces match each other so perfectly that the star can seem stable. Yet the peace is temporary, because the star is spending its future every second it shines. The sun can live for about 10 billion years, because it burns its fuel slowly. A much heavier star does not get that luxury. More mass means stronger gravity at the core. Stronger gravity demands higher pressure and higher temperature. The star answers by burning faster. That is the first strange rule. The largest stars do not live the longest. They die young. A star many times heavier than the Sunday may burn through its main supply of hydrogen in only a few million years. On human scales, that is almost forever. In cosmic time, it is a brief flare. The star is born, blazes with overwhelming power, changes the space around it, and moves toward death before a planet like Earth could even finish one complicated chapter of biological history. A low-mass star can sit quietly for ages. A red dwarf may last far longer than the current age of the universe. Our Sun is middle-aged and steady enough to give Earth time, but the kind of star that matters for this story lives differently. Its core is a factory running too hot, and every layer above it depends on the factory continuing to work. For a long time, hydrogen fusion holds the star up. Then, the hydrogen in the core runs low. The star does not simply turn off. Gravity squeezes the center tighter. Temperatures rise again, and helium begins to fuse into heavier elements. Carbon appears. Oxygen follows. In the most massive stars, this process continues through a sequence of burning stages, each shorter than the one before. Hydrogen burning can last millions of years. Helium burning is shorter. Carbon burning may be shorter still. Near the end, the pace becomes almost frightening. A star that spent millions of years in one stage can pass through its final nuclear fuels in a tiny fraction of that time. The interior becomes layered, not like a smooth ball of fire, but like a shell structure built by pressure and heat. Hydrogen outside, helium deeper in, carbon, neon, oxygen, silicon. At the center, eventually, iron. That word matters. Iron is the turning point. Most of a star's life is possible because fusion releases energy. Lighter elements combine into heavier ones, and the process gives the core the outward pressure it needs to resist gravity. Iron does not help in the same way. Fusing iron into heavier elements does not give the star more energy. It costs energy. So when the core becomes dominated by iron, the star has reached a dead end. The furnace is still surrounded by enormous mass, but the center can no longer pay the bill. There is no slow negotiation after that. Gravity takes over. In less than a second, the core of a massive star can collapse inward. Matter falls with incredible speed. Atomic structures are crushed. Electrons and protons are forced together. Neutrinos flood out. The core shrinks from something roughly planet-sized toward something closer to the size of a city. The outer layers do not immediately understand that the support beneath them has failed. For an instant, the star is still there, but its foundation is gone. Then the collapse rebounds, stalls, revives, and in many cases drives a supernova explosion outward. The star tears itself apart. Elements built inside its furnace are thrown into space. Oxygen, carbon, silicon, iron, and heavier materials are scattered into the galaxy, where future stars, planets, oceans, and bodies may one day form. This is already one of the universe's great transformations. A star dies, and the ingredients for later life are released. But a normal core collapse supernova is not enough for tonight's threat. It can be enormous. It can outshine an entire galaxy for a while. It can leave behind a neutron star or a black hole. From a dangerous distance, it would be a serious event. Still, it is not automatically the kind of star death that could strike Earth from light years away through a narrow beam. For that, the death needs something more specific. The star has to fail in a particular way. Some massive stars die with their outer envelope still surrounding them. Others lose huge amounts of material before the end. Their own radiation can drive fierce stellar winds. A companion star can strip them in a binary system. Layer by layer, the star can be peeled down until its hot inner regions are exposed. These stripped massive stars are among the most extreme objects in the galaxy. Wolf-Rayet stars are the famous example. They are rare, powerful, and close to the end of their lives. Instead of a calm surface like the Sun, a Wolf-Rayet star can have violent winds racing outward, carrying away material at tremendous rates. The star may already have lost much of its hydrogen envelope. What remains is hotter, more exposed, and more unstable than the kind of star most people imagine when they look at the night sky. Around some Wolf-Rayet systems, gas and dust can form shells, arcs, or spirals. Those patterns may look almost decorative, but they are signs of material being thrown away before the final collapse. That loss of material matters. If a massive star keeps a thick outer envelope, any jet formed deep inside may have trouble escaping. The jet can be smothered before it breaks out. The star still dies, but the universe never sees the focused flash as a gamma-ray burst. A stripped star gives the jet a better chance. Not a guarantee, a chance. That distinction is important. Wolf-Rayet does not mean death ray. Massive does not mean Earth killer. A star can be enormous, unstable, and still die without producing a dangerous beam aimed at anyone. Astronomy is full of conditions that have to line up. Mass is one condition. Stripping is another. Rotation may be one of the most important. To create the kind of event we are interested in, the collapsing core cannot simply fall inward without structure. It needs angular momentum. It needs spin. As the core collapses, rotation can help form a disk of material around the newborn black hole, or compact object. Matter in that disk becomes incredibly hot and energetic. Magnetic fields are twisted and amplified. Along the rotation axis, energy can be forced outward into narrow jets. This is where the ordinary picture of a supernova begins to change. Instead of imagining the star exploding evenly in every direction, picture a dying core with two polar escape routes. Above and below the collapsing center, jets try to punch outward. They have to fight through the star itself. The inside of the star is not empty. It is dense, hot, and collapsing. A jet, born near the core, must drill through layers of material before it can reach the surface. If the engine dies too soon, the jet fails. If the star is too extended or too heavy in the wrong places, the jet may never escape. Energy is deposited inside the star, but no bright gamma-ray burst reaches space. Only if the jet breaks out does the event become the kind of cosmic signal we detect across the universe. That makes a gamma-ray burst less like a simple explosion and more like a successful escape. The star collapses. A central engine forms. A jet launches. The jet crosses the star. The jet breaks free. Then, and only then, high-energy radiation can race across interstellar space. A failed jet may still belong to a violent death. A successful jet becomes a lighthouse. The frightening part is how narrow the difference can be. For Earth, that difference is everything. If the energy spreads in all directions, distance protects us more effectively. If the energy is focused, a planet in the beam receives a much larger share than intuition expects. Later, we will look at the real stars people name online and separate useful examples from exaggerated claims. For now, the important point is simpler. A dangerous stellar death is not defined by one scary name. It is defined by physics. The universe does not need exaggeration. The real facts are already enough. A star can be so massive that it burns through its life quickly. Its core can build element after element until iron ends the chain. Gravity can collapse the center in less time than it takes to speak a sentence. Under special conditions, that collapse can form a compact central engine, twist magnetic fields, feed a disk of falling material, and launch jets towards space. Most of the time, Earth is nowhere near the line of fire. But the mechanism exists. The kind of star that dies the wrong way is not evil, not conscious, and not hunting us. It simply follows physics to an extreme conclusion. Gravity, rotation, fusion, magnetic fields, and collapse create a moment where a star's death is no longer only an explosion. It becomes a direction. That is why distance alone is not the whole answer. A dying star can be remote and still relevant if its final violence is narrow enough and aimed correctly. The star does not have to cross the gap. The beam does that for it. From the surface of Earth, this is difficult to accept because stars look passive. They are points. Some are bright, some faint. Even the dangerous ones seem fixed in the sky, reduced by distance to harmless light. Inside them, however, time is not still. Cores are aging. Fuel is vanishing. Shells are burning around shells. Winds are stripping outer layers into space. Companions are pulling mass away. Magnetic fields are being shaped by rotation. Somewhere, in some future collapse, one of these systems may form a jet strong enough to announce itself across the universe. The question is not whether every massive star is a threat. It is which rare deaths produce the narrowest, hardest, most violent light. That question leads us directly to the beam itself. Because once the star has collapsed, once the central engine has formed, and once the jet has broken free, the danger is no longer hidden inside the star. It is traveling through space as gamma radiation, carrying the energy of a stellar death in a form our eyes cannot see. That invisible light is where the story becomes difficult, because the word light usually makes people imagine something gentle. Moonlight, on water, sunlight through a window, a star, shining quietly above a field. Gamma rays belong to the same family, but they sit at the violent end of that family. They are not a different substance from light. They are electromagnetic radiation, just like radio waves, microwaves, infrared, visible light, ultraviolet, and X-rays. The difference is energy. A radio wave can stretch across meters. Visible light has much shorter wavelengths. X-rays are shorter still. Gamma rays carry even more energy per photon, and when they meet matter, they can do things ordinary light cannot. They can ionize atoms. They can break molecular bonds. They can force chemistry to change. That is why a gamma ray burst is not just a bright flash. Calling it bright almost makes it sound harmless, as if the universe has switched on a lamp. A burst like this is better understood as a release of high-energy radiation from one of the most extreme engines nature can build. For a few seconds, sometimes less, sometimes longer, a dying star can outshine almost everything else in the gamma-ray sky. Yet from Earth, the event may not look like a star suddenly becoming visible to human eyes. Our eyes are built for a tiny slice of the electromagnetic spectrum. They can see the glow of a candle, the blue of Neptune, the white of a cloud, and the red edge of sunset. Gamma rays pass outside that window. If the detectors did not exist, much of this violent universe would remain hidden from ordinary sight. And because gamma rays are invisible to us, it is easy to imagine the danger incorrectly. The threat is not brightness in the ordinary sense. It is energy delivered in a form the atmosphere has to absorb. Many gamma-ray bursts come from galaxies billions of light-years away and still reach our instruments. That fact alone tells you how powerful they are. If an event can be detected across such distances, the source cannot be ordinary. The universe has to be doing something extreme. But the power is only half the story. The shape of the power matters. A normal lamp shines outward in many directions. Move farther away, and its light spreads across a larger and larger area. The same amount of energy becomes thinner with distance. That is why a candle across a room is dimmer than a candle beside your face, and why even a brilliant star can become a small point when separated from us by light years. A gamma-ray burst does not behave like a simple lamp. The most dangerous version behaves more like a searchlight. Energy is concentrated into narrow jets moving outward from the collapsing star. These jets do not fill the whole sky equally. They carve paths. They point. If Earth is outside the beam, the burst may be invisible to us as a major gamma-ray event. Or far less important, if Earth is inside the beam, the detectors see something extraordinary. That single detail changes the way we think about danger. The star does not need to explode evenly toward every planet around it. It only needs to aim the wrong way once. Even that sentence can mislead, because the star is not choosing anything. There is no intention. The direction comes from rotation, collapse, magnetic fields, and the structure of the engine at the core. Along the poles, where matter may be cleared more easily, jets can escape. Around the equator, infalling material may feed the central engine instead. The result is not a perfect sphere of violence, but a focused release. To a planet inside the beam, that focus is everything. Imagine standing in a dark field while a lighthouse turns somewhere far away. If the beam points away from you, the lighthouse exists, but your world stays dark. When the beam crosses your eyes, the whole landscape changes at once. The lamp did not become more powerful in that instant. Your position changed relative to the beam. Gamma-ray bursts are not exactly rotating lighthouses in the simple human sense. But the comparison helps with one thing. Direction decides what you receive. Across the galaxy, countless explosions can happen without becoming threats to Earth. Too distant, too weak by the time they reach us, or simply pointed elsewhere. Space is vast, and most beams miss most worlds. That is why these events can be both terrifying in principle and rare as actual planetary dangers. The universe can contain a mechanism without making that mechanism likely for us tomorrow. The beam is real, the risk is conditional. A nearby enough gamma-ray burst, aimed at Earth, could damage the atmosphere in ways that matter for life. The conditions would have to line up. They do not line up often. That careful wording does not weaken the story. It keeps the fear attached to physics instead of rumor. The burst begins with what astronomers call the prompt emission. That is the first flash, the hard, high-energy signal. In many cases, it lasts seconds. Some are shorter than a human blink. Others continue longer. Astronomers often divide gamma-ray bursts into short and long classes, based partly on duration, though real objects can be messy. Short bursts are often linked to compact object mergers, like neutron stars colliding. Long bursts are strongly connected with the collapse of massive stars, the type of death we are following in this story. The long burst is the one that carries the image of a massive star dying the wrong way. At the center, the engine launches jets. Inside those jets, matter moves at relativistic speeds, close enough to the speed of light that ordinary intuition begins to fail. Shocks, magnetic processes, and collisions within the outflow can convert energy into gamma rays. The exact details are still an active field of research, because the engine is hidden inside an event too distant and too fast to watch directly the way we might watch a storm in an atmosphere. Astronomers receive the evidence afterward. A flash, a position on the sky, a fading afterglow. From those clues, the shape of the explosion has to be reconstructed. This is part of what makes gamma-ray bursts feel almost ghostly. The first event is gone before many telescopes can turn toward it. What remains is the afterglow, the fading light produced as the jet slams into surrounding material and slows down. That afterglow can appear in X-rays, visible light, infrared, and radio waves, giving astronomers a way to measure distance and study the burst after the first flash has already passed. For Earth, distance is usually our protection. Most gamma-ray bursts we detect are so far away that their light is scientifically precious, but biologically harmless. They may be among the brightest things ever seen, but space has diluted them across unimaginable scales before they reach our detectors. They can trigger instruments, produce beautiful data, and teach us about the early universe without touching the chemistry of our sky in any meaningful way. A nearby burst would be different. A burst in our own galaxy, close enough and properly aligned, would not need to deliver heat like a fire. It would deliver high-energy photons into the top of the atmosphere. The air above us would absorb much of the radiation, which is good in the immediate sense. The ground would not simply be exposed to the full beam as if the atmosphere were not there. But absorbing radiation is not the same as making it disappear without consequence. The energy has to go somewhere. Molecules in the upper atmosphere can be split apart. New chemical pathways can open. Nitrogen oxides can form and interact with ozone. The ozone layer, which normally absorbs much of the sun's harmful ultraviolet radiation, could be depleted for a time. In that way, a brief event in space can produce a longer biological problem on Earth. The flash ends. The chemistry continues. That is the core of the threat. Not flame, not impact, not a star reaching down with visible light. A change in the invisible filter above every ocean, forest, and city. The beam itself would cross the solar system at light speed. There would be no early warning from the same event, because no signal can outrun the radiation that matters. If the burst were aimed at us, the first photons would arrive before any message about them could arrive. Detectors might register the event, satellites might respond, alerts might go out, but the atmosphere would already be receiving the energy. This is another reason the threat feels different from an asteroid. An asteroid can be searched for. Its orbit can be calculated. Decades of warning may be possible for some objects. A gamma-ray burst is not a rock with a predictable path through the solar system. It is the sudden arrival of radiation from a catastrophe that may have happened thousands or millions of years earlier, depending on the distance. The past can arrive without asking the present for permission. For a long time, the burst was only on its way. Then, it is here. Every star in the night sky is already a time machine. Gamma-ray bursts turn that poetry into a hazard. The beam does not carry a warning label. It carries the original violence of the event, stretched across distance, but still moving with the authority of light. If it is weak by the time it arrives, it becomes data. If it is strong enough, it becomes chemistry. The hardest part to imagine is the scale contrast. At the source, the event is enormous. A massive star collapsing, a central engine forming, a jet punching through stellar material, radiation bursting into space. At Earth, the critical battlefield may be a thin region of air. A fragile layer of atmospheric chemistry decides whether the surface stays protected or becomes more exposed to ultraviolet light. The difference between safety and crisis is not always a wall or a shield you can see. Sometimes it is a concentration of molecules high above the ground. That is why this story has to move carefully. The beam is not magic. It weakens with distance. It must be aimed. It must be close enough. Earth's atmosphere absorbs much of the initial radiation. But, under the wrong combination of distance, direction, and energy, the burst can still matter. A fake version of this story would turn the gamma-ray burst into a visible death ray slicing through Earth. A better version is quieter. A narrow flash crosses interstellar space, touches the upper atmosphere, alters the chemical balance, and leaves life under a harsher sun. One version is easier to draw. The other is closer to the actual fear. And now that the beam itself makes sense, the next question becomes unavoidable. If such a flash ever reached us from close enough, what would Earth actually feel? Not in the dramatic language of explosion, but in the slow, chemical, atmospheric reality of a planet whose shield has just been hit. If the beam ever crossed Earth, the strangest part is what would not happen first. There would be no impact, no crater would open in the ground, no mountain of water would rise from the ocean. A gamma-ray burst is not a second sun appearing in the sky and burning cities from above. It is not a visible sword of light cutting through clouds. Most of what matters would happen in a layer of air so high that people almost never think about it, even though their lives depend on it, every day. The atmosphere would become the target. That is easy to say, but hard to feel, because the atmosphere usually seems soft. It is wind on your face, clouds moving over a field, the pressure in your ears during a flight, the blue above your head. It does not look like armor. From space, however, Earth is protected by a thin chemical skin. Compared with the size of the planet, the atmosphere is almost impossibly shallow. If Earth were the size of a large apple, the breathable layer and the protective layers above it would be thinner than the skin. Yet that fragile shell decides whether sunlight is gentle enough for life, whether harmful radiation is filtered, whether water can stay liquid, and whether the surface remains more than bare rock under a star. A dangerous burst would not have to destroy that shell. It would only have to change it. The first gamma rays would strike the upper atmosphere at the speed of light. They would not pause at the edge of the solar system. They would not slow down to announce themselves. One moment the radiation is still crossing interstellar space. The next, it is meeting nitrogen, oxygen, and ozone high above the ground. Down here, at the surface, there may be no immediate sensation at all. A person standing outside might not see the sky turn white. Someone walking through a city might not feel heat on their skin. A ship at sea would not be lifted by a shockwave. Animals would not all fall silent at the same instant. The event would be more subtle than that. And because it is subtle, it is easier to describe badly. The real threat begins with ionization. Gamma rays carry enough energy to knock electrons loose from atoms and molecules. When that happens in the upper atmosphere, the familiar ingredients of air are pushed into unfamiliar reactions. Nitrogen and oxygen do not simply remain passive. They can be broken apart, recombined, and converted into reactive nitrogen compounds. Those compounds matter because they interact with ozone. Ozone is made of 3 oxygen atoms. It is harmful near the ground in high concentrations, but high in the stratosphere. It is one of the planet's quiet miracles. It absorbs much of the sun's ultraviolet radiation before that radiation can reach the surface. Without it, land life would face a harsher star every day. A gamma-ray burst would not need to remove the whole atmosphere. It would not need to remove all the ozone. Even partial depletion could matter, because the ozone layer is not decorative, it is a filter. Damage the filter, and the same sun that has fed life for billions of years can become more harmful to the living things below. That is the first correction to the disaster movie version. The burst does not kill by staying, it kills by changing what remains. The flash could be over in seconds. The chemical consequences could last much longer. Atmospheric models have suggested that a strong enough nearby burst could deplete a large fraction of the ozone layer, and that recovery could take years. Exact numbers depend on distance, energy, angle, season, and chemistry, but the general mechanism is not fantasy. High-energy radiation arrives. The upper atmosphere is ionized. Reactive compounds form. Ozone is reduced. More solar ultraviolet reaches the ground afterward, the damage becomes a delayed consequence of light that is already gone. That delay makes the scenario feel almost unfair. Earth could receive the burst, absorb it, and continue spinning. The oceans would still move under the moon. The clouds would still drift. Cities would still light up at night. To someone who did not know what had happened high above them, the world might seem normal for a while. Then, the sky would begin doing its job less well. Ultraviolet radiation is not all the same. Some UV is mostly blocked by oxygen and ozone before it reaches us. Some reaches the surface in smaller amounts and already shapes life. Too much can damage DNA, harm cells, stress plants, and injure marine organisms near the surface of the water. Life has defenses, but defenses have limits. Tiny organisms in the upper ocean matter more than they look. Phytoplankton, for example, are microscopic, but they help support marine food webs and contribute to the planet's oxygen cycle. If increased ultraviolet radiation damaged large populations near the surface, the effect could move upward through the chain of life. Small losses at the base can become larger problems higher up. Nothing about this requires the oceans to boil. Nothing requires the atmosphere to vanish. The terrifying part is not a planet turned instantly into ash. It is a living world forced to endure a new radiation environment after evolving under the old one. A sudden shift in the sky can be enough. There may be other atmospheric effects too. Reactive nitrogen dioxide could darken the upper atmosphere slightly, reducing some visible sunlight at the surface in certain models. Nitric acid could eventually wash out in rain. Climate effects have been explored, though they are more complicated and less certain than ozone depletion. For a professional script, the safest path is not to pretend every consequence is equally proven. The strongest point is ozone loss and increased ultraviolet stress. That is already serious enough. The planet's surface is connected to the atmosphere more deeply than people usually notice. We breathe the lower air, but we live under the protection of the upper air. A process that changes chemistry overhead can reach forests, reefs, fields, skin, eyes, plankton, and soil, without ever becoming visible as a falling object. This is why the phrase "what Earth would feel" is almost misleading. Earth as a rock would feel very little. Earth as a biosphere could feel a great deal. The distinction matters. A gamma-ray burst is not a threat to the planet's orbit. It would not knock Earth away from the Sun. It would not crack the mantle or stop the rotation. The Moon would continue its path. The seasons would keep arriving. Gravity would remain unchanged. The target is not the rock. The target is the conditions. Life exists inside a narrow range of permissions. Temperature must be right enough. Water must remain available. Chemistry must remain usable. Radiation must stay within limits. Every living thing on Earth depends on the fact that the surface is not fully exposed to space. A gamma-ray burst threatens that permission structure. If the burst were weak or too distant, the atmosphere would absorb it and recover without catastrophe. If it was strong and close enough, the upper air could be altered beyond the comfort zone of many species. That is why distance, direction, and energy cannot be separated. A beam from across the visible universe is a discovery. A beam from the wrong part of the Milky Way would be a different category of event. A nearby gamma-ray burst would be one of those cases where timing and direction become everything. In a mass extinction, the first damage does not have to kill every organism directly. It can remove the food source for something else. It can weaken reproduction. It can change competition. It can make survival depend on shelter, depth, season, or chance. The biosphere is a web, and a gamma-ray burst would pull on the web from above. This is why scientists have considered whether an ancient burst could have contributed to past extinction events. The idea is not that a gamma-ray burst leaves a giant crater with a label beside it. It would leave a much more difficult signature. Patterns in extinction, possible chemical changes, climate clues, and biological damage consistent with increased ultraviolet exposure. That uncertainty will matter later. For now, the important point is simpler. The danger does not need to be visible to be physical. Chemistry is physical. Radiation is physical. DNA damage is physical. A planet can be changed by something no human eye can see. In some ways, a gamma-ray burst would be more like a global environmental shock than an impact. The event from space is brief, but the problem afterward belongs to Earth systems. Atmosphere, sunlight, ocean surface, biological repair, and ecological resilience. A rock hits once. A damaged ozone layer changes every sunrise. That line is the heart of the scenario. Imagine the morning after the burst, not as a scene of burning ruins, but as a normal sunrise over a world whose protective filter has been weakened. The sun climbs over the horizon. Birds move, waves break. People wake up. From the ground, the day may look ordinary, yet ordinary sunlight is now carrying a stronger ultraviolet burden. That is how a star light years away could matter after the star itself is no longer part of the story. The dying star provides the trigger. Earth provides the consequences. The flash writes a change into the upper air, and then the sun keeps reading that change back onto the surface day after day. One brief arrival can alter the shield, and once the shield is weakened, our own star becomes the longer-lasting source of stress. The atmosphere would save the surface from the immediate radiation, but it would pay a chemical price. The ground would not receive the burst the way a bare rock in space would. That is good. Yet the same protective system that absorbs the hit becomes the system damaged by absorbing it. Protection is not always free. The shield can take the blow and still be wounded. From here, the story has to move from atmosphere to life, because the real question is no longer whether the gamma rays touch the ground. Most of them would not. The atmosphere stands in the way. The deeper question is, what happens to the living world after the sky has absorbed the burst for us, and after that protection has been weakened in return? The flash would be over, the star would be silent, the beam would have passed. But on the surface below, life would be left under a changed sun. A changed sun would not look different at first. That is the quietest part of the disaster. People often expect danger to announce itself with color, sound, or heat. A red sky, a burning horizon, a shockwave moving over the land. But ultraviolet radiation does not need drama to do damage. It can arrive inside a perfectly ordinary morning, carried by sunlight that still feels warm, familiar, and almost kind. Life on Earth has always lived under radiation. The sun is not gentle just because it gives us daylight. It sends a wide range of energy into space, and Earth survives under it, because the atmosphere filters the worst parts before they reach the surface in full strength. Every forest, every reef, every field of grass, every animal body is living beneath a compromise. Enough sunlight comes through to power life. Enough harmful radiation is blocked to let that life continue. Damage the filter, and the compromise shifts. The first victims would not necessarily be the largest animals. They might be small, exposed, and easy to overlook. Organisms near the surface of the ocean. Young plants, eggs, larvae, microbes. Thin-skinned life that cannot hide under soil, deep water, or shade. This is why an extinction from above would not feel like a single blade cutting everything down. It would be uneven. Some species would be sheltered by depth, behavior, season, or luck. Others would stand directly under the changed sky. A creature living in deeper water might be protected by the water itself. An animal active at night might avoid some of the daily ultraviolet stress. Seeds buried in soil could wait through the worst period. But life at the surface, especially life that depends on sunlight and cannot simply move away, would face a harsher world. The ocean is the place where this becomes especially important. From a distance, the sea looks like protection. It is deep, heavy, and dark below the surface. Yet the upper layer of the ocean is also one of the most important living zones on Earth. There, sunlight feeds microscopic organisms that form the base of marine food webs. Phytoplankton are small enough to vanish from imagination, but the rest of the ocean depends on them far more than their size suggests. They drift near the surface because they need light. That same choice makes them vulnerable to changes in ultraviolet radiation. If the ozone layer were badly weakened, more harmful UV could penetrate the top of the water. The effect would not need to sterilize the entire ocean. It would only need to injure enough of the productive surface layer to ripple outward. Less plankton can mean less food for tiny animals. Less food for tiny animals can mean pressure on fish. Pressure on fish can reach birds, mammals, and people. A food chain does not fail only at the top. Often, the most dangerous damage begins at the bottom, where almost no one is looking. On land, the pattern would be different but connected. Plants depend on sunlight, but they are also vulnerable to radiation stress. Increased UV can damage cells, affect growth, alter reproduction, and place extra pressure on ecosystems already balanced by temperature, water, soil, and competition. Some plants would tolerate it better than others. Forests would not necessarily fall at once. Grasslands would not all vanish in a week. The danger is pressure over time. Biology can repair damage, but repair costs energy. If the environment keeps applying stress, survival becomes harder. Reproduction may drop. Young organisms may fail more often. Populations that were already near the edge could slide downward. A world does not have to become instantly unlivable to become biologically dangerous. This is the part of cosmic disaster that our imagination tends to skip. An asteroid gives us one violent moment and then a chain of aftermaths. A gamma ray burst would be almost the reverse. The violent moment is far away and brief. The aftermath is the main event here on Earth. The flash would not choose which species to harm. It would change the rules, and every living thing would meet those rules differently. Large animals might survive the first phase easily. A deer under a forest canopy, a whale below the surface, a human inside a building. None of them would necessarily experience the burst as an immediate threat. But ecosystems are not built from isolated survivors. They are built from relationships. Remove enough plant productivity, and herbivores feel it later. Damage enough plankton, and the ocean feels it later. Change the chemistry of the atmosphere, and rainfall, sunlight, and surface conditions may carry the effect into places that were never directly touched by gamma radiation. That is why the word extinction has to be handled carefully. A gamma ray burst would not be a magic switch that turns life off. It would be a stress event. Under the wrong conditions, that stress could become global, severe, and long enough to push many species past their limits. The planet would remain alive. Microbes would survive. Deep ocean ecosystems might be far better protected. Buried life, sheltered life, and adaptable life would have advantages. The question is not whether every organism dies. The question is how much of the biosphere gets forced through a narrow doorway at the same time. Mass extinctions are rarely simple. They are usually combinations of stress, climate shifts, ocean chemistry, habitat loss, volcanism, impact winter, oxygen changes, or food web collapse. A gamma ray burst, if it played a role in Earth's past, would likely belong to that family of indirect pressure. It would not leave a neat hole in the ground. It would leave a more difficult trail, written in biology and chemistry. Scientists have explored whether an event like this could be connected to one of the ancient extinction episodes, especially the late Ordovician extinction hundreds of millions of years ago. That period saw major losses in marine life. And some researchers have considered whether a burst could have damaged the ozone layer and increased ultraviolet stress on organisms living near the ocean surface. But considered does not mean proven. That distinction is important. There is no confirmed gamma-ray burst crater. There is no simple fossil layer that says, "Here is the beam." The idea remains a hypothesis. Interesting, because the mechanism is physically plausible, but not settled as the explanation. Other causes, including climate and sea level changes, are central to how scientists discuss that extinction. A gamma-ray burst is one of those threats that would be hard to identify after the fact. An asteroid leaves shocked minerals, a crater, ejector, and a global layer that can be measured. A nearby supernova might leave traces of unusual isotopes. A burst of gamma radiation, however, interacts with the atmosphere and then disappears. The light does not remain. The beam does not leave a tunnel through space. Its most important effects may be temporary chemical changes and biological consequences. Evidence would be indirect. Patterns of extinction, possible changes in atmospheric chemistry, clues in sediments, the distribution of organisms that suffered most. Even then, other explanations could compete. This makes the event more haunting, not less. A planet might be wounded by a star, and later struggle to prove exactly what happened. A gamma-ray burst would be the kind of catastrophe that hides in those fragments. Not because it is imaginary, but because it leaves the wrong kind of scar. That is very different from saying, "It definitely happened." The honest position is narrower. If a close, well-aimed burst struck Earth, it could produce atmospheric effects capable of damaging life. Whether such an event caused a known mass extinction remains uncertain. The power of the idea comes from the possibility, supported by physics, not from pretending the case is closed. For the living world, the experience would be slow enough to become confusing. Suppose the ozone layer were significantly weakened. The next days might not look apocalyptic. The world would not necessarily wake under a blackened sky. Some regions might notice changes faster than others. Latitude, season, cloud cover, altitude, and ecosystem type would all matter. High mountains already receive stronger UV than lowlands. Clear, shallow water is different from muddy water. A polar spring is different from a tropical noon. The disaster would have geography. It would have timing. It would have uneven edges. Some of the worst damage might happen where life is most exposed during sensitive stages. Eggs near the surface, larvae in bright water, sprouting plants, microbes that cannot retreat. The visible animals people care about most might only reveal the damage later, after the bottom of the food web has changed. The fear, then, is not that everyone instantly dies beneath a flash from space. The fear is that the planet's protection changes faster than life can comfortably adapt. A gamma-ray burst, if severe enough, would be one more cosmic editor. Not the end of Earth, not the end of all life. A forced rewrite of the surface. The atmosphere is thin. The ozone layer is thinner still. The chain between sunlight and life is delicate. When we say a star could destroy Earth from light years away, the truest meaning is not that the planet becomes dust. It is that a distant stellar death could damage the conditions that make this planet recognizable to the life living on it. That kind of destruction is quieter. It does not satisfy the dramatic image. But it is the version worth understanding. The next question is whether Earth has ever actually faced something like this. Not in fiction, not as a warning invented for a title. Somewhere in the long record of life, did a beam from a dying star ever cross our planet and leave behind a wound so strange that we are still trying to recognize it from the fossils and chemistry that survived? If a beam like this can wound a planet without leaving a crater, then the next question becomes uncomfortable. How would we ever know if it had already happened. Earth is old enough for almost every strange possibility to have had time to try its luck. Continents have split. Oceans have opened and vanished. Ice has reached toward the equator. Asteroids have struck with enough force to change the future of life. Through all of that, the planet has kept only a broken diary. Rock is recycled by plate tectonics, seafloor is swallowed back into the mantle. Sediments are buried, heated, folded, eroded, and broken. Fossils appear only when the conditions for preservation are right. And even then, they give us a record full of gaps. To read the deep past, scientists have to work like detectives arriving long after the crime scene has been rained on, burned, buried, and built over by time. An asteroid helps them by being rude. It leaves impact glass, shocked minerals, a crater if the surface survives, and sometimes a global layer of unusual material. The Chicxulub impact, tied to the end Cretaceous extinction, did not simply pass through the Earth system and vanish. It left fingerprints strong enough to follow across continents. A gamma-ray burst would be more difficult. The beam would not dig a hole. There would be no obvious circle on a map saying, "Here is where the star hit Earth." The radiation arrives, interacts with the atmosphere, changes chemistry, and then the original signal is gone. Light does not remain in the rocks. The photons that caused the damage are absorbed or pass away. What might be left is secondary. Altered atmospheric chemistry, possible nitrate deposition, changes in ultraviolet stress, climate effects, and biological patterns that may or may not be unique. That is a much harder story to prove. The past may contain events we can describe physically, but cannot identify with certainty after hundreds of millions of years. This is why the question has to be asked carefully. We should not say that Earth has definitely been hit by a deadly gamma-ray burst. We also should not pretend the idea is nonsense, just because it is hard to prove. The science lives in the middle ground. A nearby gamma-ray burst is physically capable of damaging the ozone layer. That part is not the wildest claim. The uncertain part is whether one actually caused a known mass extinction. The most famous suggestion points back roughly 440 million years to the late Ordovician mass extinction. At that time, life was still mostly ocean-based. The world had no forests, dinosaurs, mammals, birds, or human beings. The continents looked different. The atmosphere was different. The biosphere was younger and more concentrated in the sea. Then, a major extinction struck. Many marine groups suffered heavily. The event is usually linked to climate change, glaciation, sea level fall, and later environmental shifts as the climate changed again. Those explanations are not minor. They are central to the standard picture. A gamma-ray burst is not needed as a magical replacement for all of them. But some researchers have asked whether a burst could have acted as a trigger. That word matters. Trigger, not necessarily the only cause, not necessarily the whole story. A trigger can push a system that is already vulnerable. If a gamma-ray burst damaged the ozone layer, increased ultraviolet radiation could have hit surface waters and shallow marine ecosystems. At the same time, chemical changes in the atmosphere could have affected climate. In some models, nitrogen dioxide formed after the burst could reduce sunlight reaching the surface, especially in certain regions, adding a cooling pressure. Rain out of nitric acid and nitrate deposition have also been explored. The basic idea is not that the gamma-ray burst left one simple mark. It is that the burst may have started a chain, first the beam, then atmospheric chemistry, then ozone loss, then increased ultraviolet radiation, then biological stress, especially for organisms near the ocean surface, possibly additional cooling effects. After that, extinction patterns in the fossil record might show the result. This is interesting, because the late Ordovician extinction affected marine life in a world where many organisms lived in shallow seas. If increased UV became a major stress, creatures closer to the surface or dependent on surface productivity could be hit harder than life, with better shielding. But again, this is not a solved case. The fossil record is complicated. Sea level changes can remove habitat, glaciation can cool oceans and lock water into ice. Ocean chemistry can shift. Different groups respond in different ways. A gamma-ray burst hypothesis has to compete with all of that. And the further back in time we look, the harder it becomes to isolate one cause. A professional version of this story should make that uncertainty part of the tension. The mystery is not weaker because the answer is not final. It is stronger because the evidence does not behave like an ordinary disaster. Imagine trying to prove that a flash of radiation crossed Earth hundreds of millions of years ago. You cannot point to the star. It may be gone. You cannot find the beam. It moved on at light speed. You cannot scrape the photons out of a cliff. What remains is a planet that may have reacted, life that may have suffered, and a record that has been damaged by time. So scientists look for what the burst would have done, not for the burst itself. Atmospheric models are one tool. They ask a controlled question. If Earth received a certain amount of gamma-ray energy from a certain direction, what would happen to the atmosphere? How much ozone would be depleted? How long would recovery take? Would nitrogen compounds create climate effects? How sensitive are the results to latitude and season? Those models do not prove a burst happened. They show whether the mechanism could work. That distinction is one of the most important pieces of the whole video. A model can say, under these conditions, the atmosphere would respond this way. It cannot, by itself, point backward and declare that the late Ordovician extinction was caused by a gamma-ray burst. For that, the atmospheric possibility has to match geological and biological evidence better than other explanations. Even if the hypothesis remains uncertain, it teaches us something important. Earth's history is not only shaped by the things that leave obvious scars. A planet can be influenced by radiation, particles, chemistry, magnetism, solar activity, nearby supernovae, and the long movement of the solar system through the galaxy. Some events carve wounds into the crust. Others touch the atmosphere and vanish. A crater is not the only kind of footprint. That idea changes how we think about cosmic safety. For most of human history, the sky looked eternal. Stars moved in patterns. Planets wandered. Comets appeared as omens because people could see them. The invisible universe had no role in ordinary fear because there was no way to know it existed. Gamma rays, cosmic rays, neutrinos, gravitational waves. All of those required instruments before they became part of science. The danger was not invented when we built the detectors. The detectors simply gave us senses we did not have. If an ancient gamma-ray burst hit Earth, no creature alive at the time understood it. There were no telescopes, no satellites, no warning systems, no records written by observers. Life would only experience the environmental consequences. The cause would be silent, distant, and unreachable. That is one reason this scenario feels so different from an asteroid. An asteroid is local by the time it matters. It is here. It crosses Earth's orbit. It enters the atmosphere. It strikes. Even if nobody can stop it, the disaster happens in the same physical neighborhood as the damage. A gamma-ray burst may come from a star that died thousands of light years away. The cause belongs to deep space. The effect belongs to Earth. Between them is nothing but light crossing time. Could it have happened before? Statistically, the galaxy is old enough, and Earth is old enough, that nearby energetic events are not absurd. The Milky Way has formed and killed massive stars for billions of years. Long gamma-ray bursts are rare in galaxies like ours today, and dangerous alignment is rarer still. The question is whether any event close enough powerful enough, and aimed correctly, struck during a vulnerable period of Earth's history. No honest answer can turn that into certainty. The correct answer is possible, not proven. That may sound less dramatic, but it is far more useful. In science, a possible mechanism becomes serious when it makes testable predictions. If a burst depleted ozone, surface UV should rise in ways that affect exposed organisms. If atmospheric nitrogen chemistry changed, there may be chemical consequences. If climate cooling followed, geological records should be consistent with that timing. Researchers can compare these ideas against fossils, sediments, climate indicators, and competing causes. The case can strengthen, the case can weaken. That is how it should work. For our story, the late Ordovician hypothesis becomes a window rather than a verdict. It lets us imagine what a gamma-ray burst would mean for a real planet. Without pretending, we have solved the entire ancient extinction. The surface around us is not proof that the universe has always been gentle. It is proof that life has endured whatever reached it. Some threats failed to sterilize the planet. Some may have reshaped it. Many left clues that are hard to read. A gamma-ray burst, if it ever struck, would belong to that last category. A cosmic event whose strongest signature may be a biological pattern rather than a crater. That is why the next part of the story has to become more specific. We cannot leave the danger as an abstract beam from somewhere. People naturally want suspects. They want names. They want to know whether a star in our own sky could be the one. That is where the internet often becomes careless. Certain stars are repeated as if they were confirmed death machines. Betelgeuse, Eta Carinae. W are 104. Each one is real and fascinating. Some are massive, unstable, and close to dramatic endings in astronomical terms. But real danger depends on more than a scary name. Distance matters. Direction matters. The chance of a jet escaping matters. The alignment with Earth matters most of all. So before this story can go any further, we need to look at the suspects carefully, not to make the sky feel fake safe, and not to turn every bright massive star into a countdown, but to separate what is known from what is repeated, because it sounds terrifying. Now the story reaches the part where fear usually becomes careless. Once people hear that a dying star could send a beam across space, they naturally want a name. A nameless threat feels too abstract. A named star feels like evidence. It becomes easier to point toward Orion, or Carina, or Sagittarius, and imagine that one particular light in the sky is already waiting to become the weapon. This is where a calm documentary has to slow down. Not because the stars are harmless, because the truth is more precise than the rumor. A dangerous star is not dangerous simply because it is famous. It is not dangerous because it is large, red, unstable, beautiful, or close to death in astronomical language. To matter for Earth, several difficult conditions must line up together. The star has to die in the right way. The event has to produce a jet. The jet has to escape the star. The beam has to be energetic enough. The distance has to be close enough. And most importantly, the beam has to point toward us. Remove one of those conditions and the story changes. The star may still be spectacular, it may still be scientifically important. It may still end in an explosion that future astronomers would watch with awe. But awe is not the same as danger. The first suspect people often mention is Betelgeuse. It is easy to understand why. Betelgeuse is one of the most famous stars in the sky, a red supergiant glowing in the shoulder of Orion. It is enormous. If placed at the center of our solar system, its outer layers would reach far beyond the orbit of Mercury. It has burned through its life quickly, swollen into a vast red atmosphere, and will one day collapse and explode as a supernova. That sentence sounds like the beginning of a disaster. But for Earth, Betelgeuse is not the star in this title. Its future supernova would be extraordinary to see, not something that should be treated as an extinction warning. It is hundreds of light years away. The exact distance has been debated and refined, but it is not sitting in the dangerous neighborhood usually imagined for a direct supernova threat. More importantly, Betelgeuse is not the classic candidate for the kind of long gamma-ray burst we have been building toward. It is a red supergiant, not a stripped Wolf-Rayet star with the same conditions expected for a clean, relativistic jet. When Betelgeuse finally explodes, the night sky may change in a way no human generation has ever witnessed. For weeks or months, a new bright object could appear where Orion now holds a familiar red point. The event would be scientifically priceless. That would be wonder, not doom. Still, Betelgeuse teaches an important lesson. Fame can distort danger. It feels close to us emotionally, because people know its name and have seen dramatic headlines about it. But emotional closeness is not astrophysical closeness. A star can dominate human imagination and still be too far, too wrong in type, or too badly aligned to be the threat we are describing. Another name carries a heavier atmosphere: Eta Carinae. Eta Carinae sits in the southern sky, but in astrophysics, it is one of the most dramatic stellar systems in our galaxy. It is not a quiet red giant fading toward collapse. It is a massive, unstable, luminous system wrapped in the wreckage of its own violence. In the 19th century, Eta Carinae underwent the Great Eruption. For a time, it became one of the brightest stars in the sky. It did not die. Instead, it threw off an enormous amount of material and survived, leaving behind the Homunculus Nebula, two lobes of gas expanding away from the star system like the frozen imprint of an explosion that was not quite a supernova. This makes Eta Carinae feel like a better suspect. If someone wanted a real star that feels as if it belongs in a cosmic hazard story, Eta Carinae is hard to ignore. But again, the details matter. Eta Carinae is thousands of light years away. Its future is uncertain in timing and exact form. It may eventually explode as a supernova, perhaps an unusually powerful one, but a normal supernova at that distance is not the same as a nearby beam aimed at Earth. Studies that have examined the hazard have generally found that Eta Carinae is unlikely to produce the kind of Earth-threatening event people imagine, especially because distance and orientation reduce the danger. The system is dangerous in the sense that it is one of the most violent stellar objects in the Milky Way. It is not a confirmed countdown aimed at us. That is a very different statement. This distinction is important for trust. If a script says Eta Carinae will destroy Earth, viewers who know the subject will immediately hear slop. If the script says Eta Carinae is a massive, unstable system that shows how extreme dying stars can become, but that current evidence does not make it a credible Earth-ending threat, the story becomes stronger, not weaker. Professional science writing does not have to be less interesting. It just has to make the right thing interesting. Eta Carinae is a suspect that teaches the rules even if it is not convicted. Then there is WR104. This is the one that once received the kind of nickname that almost guarantees panic: the Pinwheel Death Star. Unlike Betelgeuse, WR104 is a Wolf-Rayet system. Unlike many distant theoretical examples, it has a striking shape that can be shown visually: a spiral of dust, created as powerful stellar winds from two massive stars interact while the system orbits. The result looks almost too perfect, a rotating pattern in infrared light, as if the star system is drawing a spiral into space before it dies. For years, WR104 became famous because of the possibility that its rotational axis might be pointed close to Earth. If a Wolf-Rayet star in that system eventually produced a long gamma-ray burst, and if the jet followed that axis, then alignment would matter. The visual pinwheel made the system feel like more than an abstract possibility. It looked directional. It looked aimed. That is why it spread. But astronomy does not freeze at the first scary headline. Observations improve. Models change. Instruments collect more detail. And recent work has complicated the old fear. New measurements of the WR104 system suggest that the orbit of the stars is angled away from us, not lined up as cleanly as earlier interpretations made it seem. That does not make WR104 boring. In some ways, it makes the system more scientifically interesting, because the pinwheel and the orbit may not be arranged as simply as expected, but it weakens the extinction story. Again, the rule returns. A dangerous-looking star is not enough. The beam has to point here. If WR104 is not aimed at Earth, then even a dramatic future death becomes a spectacle somewhere else, not a direct biological hazard for us. A gamma-ray burst can be devastating along its path and irrelevant outside it. That is the strange cruelty and mercy of beaming. It can make distance less comforting for worlds inside the jet, while making even violent events harmless for worlds just outside the line. This is why the suspect list has to be treated like an investigation, not a countdown. Betelgeuse shows how fame creates false urgency. Eta Carinae shows how genuine violence can still fail to become an Earth threat. WR104 shows how alignment can make or break the entire story. Together, they teach the viewer how not to be fooled. A star can be massive, unstable, and close to death in astronomical terms, while still posing little risk to Earth. It can be called terrifying in a headline, while the actual risk remains low. The real threat is narrower, rarer, and more conditional. That may sound comforting, but it should not make the topic feel small. Rare events matter in astronomy because the universe has time. A single human life is short. A civilization is short. The age of Earth is not. Across hundreds of millions of years, rare things get chances to occur. The danger is not that one famous star has a date written on it. The danger is that the galaxy contains mechanisms that can hurt planets under the right geometry. The sky is not full of immediate death beams. It is full of physics. Some of that physics is gentle enough to make planets. Some of it is violent enough to strip atmospheres, forge heavy elements, collapse cores, and fire jets across interstellar space. Our job is to tell those apart. The nearest dramatic star is not always the most dangerous one. Distance is crucial, but not alone. A closer star with the wrong type of death can be less threatening than a farther one with a strong, well-aimed beam. A famous star visible to the naked eye can be less relevant than a faint system most people have never heard of. Danger is not brightness. Danger is not fame. Danger is energy, distance, direction, and mechanism. The most unsettling candidate may not be the one with the best name. It may be an object buried in a catalogue, poorly known, faint behind dust, or not yet recognized as a future jet source. Massive stars often live in crowded, dusty regions of the galaxy, where distance, orientation, and internal structure are hard to determine. Some of the most important details are hidden until the star dies. That uncertainty should not be inflated into panic, but it should keep the story honest. We know enough to say that a close, aligned gamma-ray burst would be dangerous. We do not know every future collapse in the Milky Way with perfect confidence. Astronomy is not a list of final answers. It is a map that improves with every instrument. The important thing for Earth is that no known nearby star is currently confirmed as a gamma-ray burst threat aimed at us. That sentence should be said clearly, because viewers deserve it. But it should be followed by the deeper truth. The absence of a known confirmed threat does not erase the mechanism. It simply means the named suspects people repeat online are usually weaker than the fear built around them. The fear moves from one celebrity star to a larger question. How many massive stars are out there? How many will die with jets? How many jets will point towards some planet? How close would one have to be to matter? And how often, over geological time, does a living world find itself in the wrong place in the beam? That is where the story becomes bigger than Betelgeuse, Eta Carinae, or WR104. The named suspects help us learn the rules, but the rules are the real subject. A gamma-ray burst is not dangerous because a headline says so. It is dangerous because energy that would normally be spread thin can be concentrated into a narrow path. So the next step is to leave the celebrity stars behind and focus on the geometry itself. Because in this story, direction may be the difference between a harmless flash in a distant sky and a biological crisis on a living world. Direction is the hidden variable in this whole story. It is the part that makes the danger feel almost unfair. A star can explode with unimaginable force and still mean nothing to Earth if most of its energy spreads elsewhere. Another event, not necessarily closer in the way our instincts care about, can become more important because its violence is squeezed into a narrow path. The universe is not only a question of how much power exists, it is also a question of where that power goes. That is why the same gamma-ray burst can be two completely different things at once. For most of space around it, it is an explosion that happened somewhere else. For a world inside the beam, it is the sky changing. This is not how ordinary fear works. When a storm approaches, distance is the main comfort. When a fire is far away, distance protects. A gamma-ray burst changes the scale. The star may remain far beyond any human journey, but its radiation still draws a line through space. Most places are not on that line. That is the mercy. A few places may be. That is the threat. Imagine two explosions with the same total energy. The first releases its energy in every direction, like a sphere expanding into the dark. As the sphere grows, the same energy has to cover more and more area. Space dilutes violence. Now, force much of that energy into a narrow cone. The total energy may be similar, but a planet inside the cone receives a far greater share than it would from a spherical blast. Outside the cone, the event may be much less impressive. Inside it, distance feels smaller than it would have felt otherwise. The beam does not break the laws of physics. It concentrates them. This is why astronomers care so much about beaming. A gamma-ray burst observed from Earth appears astonishingly bright, partly because we are seeing it along or near the direction of the jet. Its apparent brightness depends on the geometry between the jet and the observer. The observer matters. That idea is strange in a universe that usually makes us feel insignificant. Earth is not the center of anything. Massive stars do not arrange their deaths around our planet. Yet for a beamed event, the observer's location decides what kind of universe they experience. A gamma-ray burst aimed elsewhere can be a silent event to us. A burst aimed here becomes a flash in our detectors. And if close enough, something more serious. Many gamma-ray bursts may occur with jets that never point toward Earth. We do not see the full prompt flash because the radiation is not aimed at us. In a beamed universe, what we observe is only a selection of what occurs. The Milky Way could contain past stellar deaths whose jets missed us completely. For Earth, those events are almost irrelevant. For another planet somewhere along one of those paths, the same event might have been the most important day in its history. Direction turns a cosmic explosion into a private disaster. That is the part that distance alone cannot explain. A star, 10,000 light-years away, may sound absurdly remote. Even light needs 10,000 years to cross that gap. But gamma rays travel at the speed allowed by the universe itself. Once emitted, they are already on the fastest road. No alarm can outrun them. If the beam is aimed at Earth, the first warning is not a message from the star. It is the arrival of the radiation. Satellites may register the flash, ground teams may receive alerts, but the photons that matter have already reached the atmosphere. The event is not approaching after we notice it. Notice and arrival are nearly the same thing. That makes gamma-ray bursts different from almost every familiar planetary defense problem. An asteroid has an orbit. A comet can be tracked as it brightens. Solar storms give some warning once the sun erupts, because particles and plasma travel slower than light. A gamma-ray burst from deep space gives no practical early warning from the same event, because the dangerous signal is the messenger. The only real preparation is understanding the population of stars and watching the sky. That may sound helpless, but it is also honest. There are cosmic hazards we can imagine deflecting. There are others we can only study, measure, and place into context. A nearby aligned gamma-ray burst belongs much closer to the second category. The defense is not a shield in orbit. The defense is knowledge. Still, the geometry remains the center. Even a dangerous type of star becomes irrelevant if its axis points away. A less famous object could become more important if its axis points toward us. This is why the named suspects from the previous part cannot be judged by fame alone. Betelgeuse, Eta Carinae, and WR104 attract attention for different reasons, but the actual hazard calculation is colder than a headline. It asks for angle, distance, collapse type, jet width, and how much energy would reach Earth after crossing the gap. A scary title collapses those questions into one feeling. Real astronomy pulls them apart again. The width of the beam is especially important. A narrow jet can make the burst look brighter to anyone inside it, but it also means fewer planets are struck. A wider jet covers more of the sky, but the energy may be spread differently. Gamma-ray burst jets are not all identical. Their opening angles, energies, structures, and environments vary. A planet does not need to sit at a perfect center line for the event to matter, but being closer to the strongest part of the beam can change the outcome. Near the edge, the received energy may be lower. Far outside, the burst may be harmless. Geometry becomes a gradient, not just a yes or no switch. That detail matters because real space is messy. Stars are not laboratory devices. They rotate, lose mass, interact with companions, throw off winds, and die inside environments shaped by their own lives. A jet may not be perfectly smooth. The material around the star may absorb, scatter, or reprocess energy. The afterglow can tell astronomers something about that environment, but it never gives the simple comfort of a cartoon beam drawn with clean edges. The danger is precise in concept and messy in reality. A beam is the reason distance can fail to feel safe. Messiness is the reason no simple internet claim should be trusted without evidence. This is also why a gamma-ray burst can be seen across the observable universe. When a jet points toward us from a distant galaxy, the energy is focused along our line of sight. The event can be so bright that instruments detect it even after billions of years of travel. Those distant bursts are not threats because they are too far away, but they reveal the scale of the engine. Every distant burst is a demonstration, not of danger to Earth, but of the mechanism. A flash from a galaxy billions of light years away says, this kind of focused violence exists. Then the mind naturally asks, what would happen if the same kind of thing occurred much closer? That is not panic. That is scale. Move the source from a distant galaxy into the Milky Way. Aim it properly. Keep it powerful enough. Suddenly, the abstract flash becomes an atmospheric question for Earth. The entire story turns on those conditions. Direction is not only important at the source, it also matters at Earth. A burst hitting one side of the planet would affect the atmosphere differently depending on where the beam arrived, what season it was, and how global circulation spread the chemical consequences. The hemisphere facing the burst receives the initial radiation. Atmospheric chemistry then becomes a planetary process rather than a single point of impact. Latitude, sunlight, and circulation all influence how the wound develops. The beam may arrive in seconds. The aftermath moves through systems. That makes the event both sharp and slow. Sharp in arrival, because radiation travels at light speed. Slow, in consequence, because chemistry and ecology unfold over months and years. On that scale, direction becomes a lottery ticket written in light. Most tickets miss. One hit would matter. A planet inside the beam would not see the star choosing it. It would simply receive the geometry of an ancient collapse. Perhaps the star died before the first cities. Perhaps before humans existed. The beam would cross the dark for all that time, expanding slightly, weakening, but still carrying the signature of its origin. When it finally reached Earth, the event at the source would be old history. Here, it would become the present. That time delay can make the universe feel haunted. The cause may no longer exist in any active form. The star may have become a black hole or neutron star long before the radiation arrives. The original explosion may have faded from every nearby view. But light preserves the event and carries it outward. Space does not forget immediately. It delivers. A burst aimed at Earth would not be a future decision made by a star. It would be an old event whose consequences finally caught up to us. Distance separates the event from the damage in time, not only in space. There is no single fear radius that can be repeated without context. For a gamma-ray burst, near is not just a number of light years. It is distance plus alignment plus energy. A farther aligned burst may matter more than a closer non-aligned explosion. A closer weak event may matter less than a farther powerful one. That is why we should avoid fake certainty. Statements like "this star will kill us" or "that star is safe forever" usually hide the real variables. Better to say, based on what is currently known, no confirmed nearby gamma-ray burst source is aimed at Earth, but a close, powerful, aligned burst would be a serious atmospheric hazard. Think again about the stars in the sky. Each point seems round to us because distance removes its shape. Yet a star's final act may be highly directional. From Earth, a dangerous system could look like a faint point. The geometry that matters may be hidden inside the rotation of a core, the shape of a binary orbit, the stripping of an envelope, or the axis of a jet that does not exist until the star collapses. The night sky looks flat. The danger is three-dimensional. That is the lesson of direction. Not every powerful thing is aimed at us. Not every distant thing is irrelevant. Between those two truths sits the real story of gamma-ray bursts and Earth. We have now followed the threat from a dying massive star, through the collapse of its core, into the formation of a beam, through the atmosphere and into the living surface. The remaining question is how we would recognize such an event. In the modern universe, if the beam is invisible to human eyes and arrives without warning, how do astronomers catch it at all? That is where the story moves next. From the beam itself to the instruments watching the high-energy sky. The instruments watching that high-energy sky are, in a strange way, extensions of senses we were never born with. Human eyes cannot see gamma rays. They cannot feel a burst arriving from a distant galaxy. They cannot look at a quiet patch of darkness and know that for a few seconds, it has become the brightest place in the high-energy universe. Without machines above the atmosphere, most gamma-ray bursts would pass through human history as invisible events. That is why this danger was discovered late. Not because the universe recently became violent, because we only recently learned how to notice the violence. For most of astronomy, the sky belonged to visible light. Telescopes gathered the same kind of light our eyes could see, only with more patience and more precision. Stars became sharper, nebulae became structured, galaxies separated from the blur. But the universe was speaking in many forms at once, and visible light was only one small part of the message. Radio astronomy opened another window. X-ray astronomy opened another. Gamma-ray astronomy opened one of the most extreme. From the ground, Earth's atmosphere protects us from much of this high-energy radiation. That protection is one reason life can exist here, but it also means the surface is a poor place to study gamma rays directly. The same atmosphere that saves us from the harshest radiation also blocks our ordinary view of it. So to watch gamma ray bursts properly, detectors had to move above the air. There, in orbit, a spacecraft can wait for the sudden rise in high-energy photons. It does not know where the next burst will happen. It does not point at one star and watch it like a countdown clock. Gamma-ray bursts are not polite. They appear without warning from almost anywhere in the sky and vanish quickly. The first job is to catch the flash. That alone is difficult. The detector has to look across a wide part of the sky. It has to recognize that the gamma-ray count has suddenly jumped above the background. It has to decide that this is not noise, not a solar flare, not a charged particle hitting the instrument, but a real burst from deep space. Then speed becomes everything. A gamma-ray burst is not like a galaxy waiting millions of years to be photographed. The prompt flash is brief. By the time an ordinary telescope could slowly turn and begin observing, the highest energy moment may already be over. This is why missions designed for gamma-ray bursts are built around reaction. NASA's Swift Observatory is named almost perfectly for its task. It carries instruments that can detect a burst, locate it, and quickly turn the spacecraft so other onboard telescopes can study the fading afterglow. The burst begins in gamma rays, but the story continues in X-rays, ultraviolet, optical light, infrared, and radio. Each wavelength catches a different part of the aftermath. That afterglow is the trail. The prompt flash tells astronomers that something enormous has happened. The afterglow helps them find where. Once a burst is detected, an alert can be sent to observatories around the world. Ground telescopes may swing toward the coordinates. Space telescopes may follow. Astronomers search for a fading point of light, a host galaxy, a redshift, a distance, and eventually a physical explanation. The first seconds belong to satellites. The next hours and days belong to a global chase. A burst occurs in a galaxy that may be billions of light years away. A detector in orbit notices a sudden flash. Coordinates are distributed. Telescopes on different continents respond. Spectra reveal how much the light has been stretched by cosmic expansion. The host galaxy emerges from the background. A few seconds of violence becomes a map, a distance, and a story. Fermi plays a different but complementary role. Its gamma-ray burst monitor watches much of the sky for flashes across a wide range of gamma-ray energies, while the Large Area Telescope can observe even higher energy photons from some events. Together with Swift and other observatories, it helps build a record of bursts, how often they happen, how long they last, how bright they are, and how their signals differ. This matters because one burst by itself can mislead. A population teaches patterns. Some bursts are short, lasting less than 2 seconds. Many of those are connected to compact object mergers, such as neutron stars colliding. Others last longer and are linked to the collapse of massive stars. Then there are strange events that do not fit neatly. Long bursts with unexpected features. Ultra-long events. Bursts with unusual host galaxies and flashes that force astronomers to revise their categories. Nature rarely stays inside the first box we build for it. For Earth's safety, the monitoring does something else as well. It reminds us that most gamma-ray bursts are very far away. The bursts that fill catalogs are usually not happening in our stellar neighborhood. They arrive from distant galaxies, sometimes from so far away that the light began traveling when the universe itself was much younger. That distance turns catastrophe into information. A burst that would be lethal nearby becomes a harmless signal when it comes from across the cosmos. It can teach us about dying stars, black holes, neutron star mergers, early galaxies, and the physics of jets without threatening Earth. This is one of the strange privileges of distance. We can study violence without being inside it. But if a truly nearby aligned burst occurred, the same instruments would not give us time to stop it. They would tell us what had happened as it happened. The gamma rays would arrive at Earth, and the detectors would record the flash. Alerts could go out. Scientists could measure the energy, direction, and afterglow. Atmospheric instruments might later study changes in chemistry. The warning would be scientific, not preventative. That does not make the monitoring useless. It makes it honest. Astronomy often cannot protect by blocking. It protects by understanding probability, mechanism, and context. We learn which fears are exaggerated, which are physically possible, which are so rare that they belong to geological time, and which objects in the sky deserve continued observation. Without monitoring, every burst is either invisible or reduced to rumor. With monitoring, it becomes data. Data is what keeps this story from becoming superstition. A nearby gamma-ray burst would stand out immediately because of brightness, location, and the absence of a huge cosmological distance. Astronomers would work to localize it, search for the afterglow, identify the host or remnant, and determine whether it came from a massive star collapse or another process. But for Earth, the key atmospheric question would begin at once. How much energy reached the planet? From what direction? And what chemical response followed? The instruments in space would measure the sky. The instruments on Earth would measure the wound. Satellites already watch the atmosphere for ozone, ultraviolet radiation, and chemical changes. In a real event, those measurements would become crucial. The gamma-ray flash might last seconds, but the scientific work afterward could last years. This is another reason the event would not feel like the disasters people expect. The first announcement might be a technical alert, not a scream from the sky. The serious language would come from scientists describing fluence, spectra, localization, atmospheric chemistry, ozone depletion, and ultraviolet exposure. Those words sound less dramatic than fireball, but they may describe a deeper global problem. Still, the most important fact remains almost uncomfortable. Detection is not control. Knowing that gamma-ray bursts exist does not give us a way to prevent a nearby aligned one. No technology can move Earth out of a beam arriving at light speed. No warning can arrive before the photons. No shield could be quickly built around the atmosphere. That sounds frightening, but it also places the danger in the right category. This is not a practical emergency for tomorrow morning. It is a rare astrophysical hazard over enormous spans of time. The correct response is not panic or pretending a celebrity star is about to fire at us. The correct response is continued observation, better models, and honest public explanation. That calm is not denial, it is scale. Every day, satellites record gamma-ray flashes from somewhere in the universe. Most are far beyond any threat to Earth. Each one adds to our understanding of how massive stars die, how jets behave, how compact objects merge, and how high-energy radiation travels through space. In that sense, the dangerous mechanism also becomes a scientific tool. A burst can reveal the distant universe. It can shine through gas between galaxies. It can mark the death of a star too far away to study any other way. Some of the same physics that could harm a planet nearby helps us study galaxies we would otherwise barely see. The universe often gives knowledge and danger through the same door. If a burst happens far enough away, it is a gift to astronomy. If the same event happens close enough and aimed correctly, it becomes a hazard. The difference is not the nature of the burst. The difference is where we stand. That returns us to the central unease of the whole story. Earth is not special enough to be targeted, but it is not separate from the galaxy either. We live under a protective atmosphere, around an ordinary star, inside a stellar disk, where massive stars are born and die. Most of their deaths will never matter to us. Some will be visible. A very rare few, under the wrong alignment, could be more than visible. The instruments above Earth are our way of admitting that the sky contains events our senses cannot catch. They do not make us masters of those events. They make us witnesses, and witnessing matters. It turns a flash into a measurement into a model, and a model into a better understanding of how fragile the surface of a planet can be. By now, the shape of the threat is clear. A massive star can die. A jet can escape. Gamma rays can travel through space. Earth's atmosphere can absorb them and be chemically changed. Life can suffer afterward, not from the burst itself, but from the altered sky. Astronomers can detect similar events across the universe, usually at safe distances, and use them to understand what would otherwise remain invisible. What remains is to return to the star in the title, not a single confirmed executioner waiting above us. Something subtler, a kind of star whose death does not need to come here, because under the right conditions, its light can. The final step is to bring the whole chain together and ask what this really says about danger, distance, and the thin shield that makes Earth feel safe beneath the night. The thin shield that makes Earth feel safe is easy to forget because it has always been there for us. Every morning, sunlight arrives and the world simply accepts it. The air warms, oceans glitter, cities wake. To a human life, the sky feels permanent, almost like part of the ground turned blue and lifted above us. It does not feel fragile. It does not feel chemical. It does not feel like something that can be changed by a star we will never touch. But that is where this whole journey has been leading. The danger is not that a distant star can move Earth out of its orbit. It cannot. The danger is not that a beam of gamma radiation would crack the planet apart like stone. It would not. The danger is more subtle, because it touches the conditions that let ordinary life continue without thinking about space at all. A planet is not only a ball of rock, it is a system of permissions. The right distance from the sun, enough gravity to hold an atmosphere, oceans that can store heat and carry chemistry, air that filters radiation before it reaches the surface, a thin layer of ozone, high above the weather, quietly absorbing ultraviolet light day after day. Life does not live on Earth because space is gentle. Life lives here because Earth has protections that keep space from arriving in its raw form. A gamma ray burst matters because it attacks that truth from a distance. It reminds us that danger does not always need mass. It does not need an orbit that crosses ours. It does not need to become a visible object moving through the sky. Sometimes, the universe reaches a planet through radiation, through chemistry, through a brief signal that becomes a long consequence. The star in this story does not have to come here. That is the point. It can be thousands of light years away. It can die before anyone on Earth knows anything has happened. Its core can collapse in darkness from our point of view, while the beam begins a journey that may outlast empires, languages, coastlines, and civilizations. For all that time, Earth may be quiet. Forests may grow. Ice ages may come and go. Species may rise, vanish, and leave only traces in stone. Then the light arrives. Not as a visitor, as an event. If the burst is too far away, it becomes data. A satellite registers it. Astronomers measure it. Telescopes chase the afterglow, and the dying star becomes a lesson about black holes, jets, and the early universe. If it is close enough, powerful enough, and aimed correctly, the same mechanism becomes something else. The atmosphere absorbs the hit. The chemistry changes. The ozone layer weakens. The surface receives more ultraviolet radiation from the sun. Life below the sky has to endure the aftermath. That chain is what makes the title possible without turning it into a lie. A star could destroy Earth from light years away only if we understand destruction in the biological sense. The rock would remain. The planet would still move around the sun. The continents would not vanish. The oceans would not necessarily boil away. But the living world could be forced into crisis. That is the version worth taking seriously. Not instant fire, not a cinematic beam slicing the planet in half. A damaged shield, followed by a harsher sun. The most honest fear is not that we are doomed. It is that our safety depends on thinness. A thin atmosphere, a thin ozone layer, a thin line between sunlight that feeds life and sunlight that harms it. A thin chance that a beam points somewhere else instead of here. Most of the time that line holds. If a nearby gamma-ray burst ever struck Earth, it would not mean every living thing was instantly gone. Deep ocean life would have protection. Buried microbes would continue. Some ecosystems would be shielded by water, soil, behavior, or geography. Survival would be uneven, but uneven is not nothing. Still, resilience is not invulnerability. Many species can vanish while life as a whole continues. The planet can survive and still lose the world that existed before. That is why the question matters. Not because it gives us a date to fear, because it reveals how connected the surface of Earth is to events far beyond the solar system. A massive star dies. A jet escapes. Gamma rays cross the galaxy, the upper atmosphere absorbs them. The chemistry of the sky changes, sunlight reaches the ground differently. Food webs respond. Fossils, if enough time passes, may be the only witnesses left. A single line of radiation can become a chapter in the history of life. Some of those machines are nearing the ends of their lives. Some have already died, and their light has not yet told us. Some will collapse without much consequence for Earth. Some will produce supernovae that future astronomers may celebrate from a safe distance. A very rare few, in the right conditions, may send jets into space that become gamma-ray bursts. Most will miss us. That is not a small detail. It is one of the reasons we can exist. Space is vast, beams are narrow, and alignment is rare. The galaxy is not arranged around Earth, and that is a kind of protection. Violence happens constantly somewhere, but most of it is not pointed at our small planet. The same indifference that makes the universe feel cold also helps keep us safe. Yet ignorance would be a poor comfort. It is better to know the mechanism, better to know why distance helps, why direction matters, why the atmosphere is the battlefield, and why exaggerated claims about individual stars can be wrong, while the underlying physics remains real. That is the difference between fear and understanding. Fear says there is a Death Star in the sky. Understanding says a certain kind of massive star, under rare conditions, can produce a beamed high-energy event, and a close, aligned burst could damage Earth's ozone layer. The second sentence is less dramatic. It is also more powerful, because it is closer to the truth. That connection is what makes a calm night sky feel different after learning this. Not worse, exactly. Not ruined. Just deeper. The stars are no longer only lights. They are histories in progress. Some are young furnaces. Some are aging giants. Some are stripped, unstable, and close to collapse. Some are dead already, their final messages still crossing space. The next time you look up at Orion or the southern sky, or any dark field of stars, the fear should not be that one of them is definitely about to destroy us. That would be the wrong lesson. The better lesson is quieter. Earth is protected, but not separate. The atmosphere is strong enough to make life possible, but delicate enough to be worth noticing. The galaxy is mostly harmless to us on human timescales, but not empty of hazards. Distance usually saves us, but direction can change what distance means. The sun is our source of life, but the shield above us is what keeps that life from being overwhelmed by the wrong kinds of light. The star that could destroy Earth from light years away is not a villain. It is a reminder that life exists inside layers of protection we rarely see. A reminder that the most dangerous things in the universe are not always the things that move toward us. A reminder that sometimes the invisible matters more than the visible. And perhaps, most strangely, a reminder that a planet can be changed by something ancient. A burst could begin its journey before anyone here is watching. It could cross the dark while generations live and die beneath a peaceful sky. By the time it arrives, the source may be only a remnant. The star's death may be old news to the galaxy around it. But for Earth, arrival is the only moment that matters. That is what light does. It carries the past into the present. Most of the time, that is beautiful. The starlight entering your eyes tonight may have left its source years, centuries, or millennia ago. You are not seeing the universe as it is right now. You are seeing a layered memory, delivered photon by photon, across the dark. In the case of a gamma ray burst, the same principle becomes unsettling. Light can bring beauty. Light can bring information. Under rare conditions, light can bring damage. The universe does not separate those categories for us. We have to learn the difference. And that is why we watch. Not because watching gives control over everything, but because watching turns darkness into knowledge. It tells us which stars are ending, which flashes are distant, which fears are exaggerated, and which rare mechanisms deserve respect. Instruments in orbit are not weapons against the universe. They are eyes we built because our own eyes were never enough. Maybe that is the most human part of the whole story. We live on a small planet, under a thin shield, in a galaxy full of engines older and larger than anything we can build. We cannot command massive stars. We cannot stop a gamma ray burst once it is on its way. We cannot make the universe gentle, but we can learn its rules. We can separate panic from possibility. We can look at a frightening mechanism and describe it carefully enough that fear becomes clarity. So the next time someone says a star could destroy Earth from light years away, the answer is not simply yes, and it is not simply no. The better answer is this: a star cannot reach across space like a hand. It cannot choose us. It cannot destroy Earth just by being bright or famous. But if a massive star dies in the right way, launches a powerful jet, and that jet is aimed toward us from close enough, then its gamma rays could change the chemistry of our atmosphere. Earth would survive as a planet. Life would survive somewhere. But the world on the surface could be wounded by a flash from a star that never came near us. That is the real story. Not a prophecy, not a countdown. A rare alignment of physics, distance, and direction. And beneath that story is something almost peaceful. Tonight, the atmosphere is still here. The ozone layer is still quietly doing its work. The sun will rise again, behind the same invisible protection. Far away, massive stars are living out their short, bright lives, and almost all of their violence will pass into space without ever touching us. For now, Earth is still inside its shelter. For now, the dangerous beams are elsewhere. For now, the night sky remains calm enough to look beautiful. Thank you for watching this journey through one of the quietest and most powerful dangers in the universe. If you enjoyed it, leave a like, subscribe for more calm space documentaries, and write in the comments what part of the universe you want us to explore next. Wherever you are watching from, whatever time it is for you right now, I hope the sky above you feels a little deeper than it did before. Good night.